Welcome. My name is Renee McCormick. I'm the Executive Director of the National Math and Science Initiative, and I'm really glad you're here. This is the very first screencast, for lack of a better word, in the series of screencasts to help you better navigate the AP Chemistry course. This is in no way to take the place of an actual teacher. I don't want to be your teacher. I just want to be sort of like the man behind the curtain in The Wizard of Oz. I want to be that voice that's going to help you understand things because very, very few of us are capable of learning something the very first time it's presented to us. I have strongly believe that everyone has the ability to learn. It just comes down to repetition. So you may have to hear the material more than once. You may have to hear it many, many times, and there's no disgrace in that. I'm a pretty slow learner and I have mastered this stuff, but it has been a journey. It has not been a single event. So let's dig in. Chemistry. What is a chemistry course? Well, a chemistry is a course should involve the study of both matter and energy. If you took a first year chemistry course, it primarily dealt with matter, and matter, with just a little bit of energy. But in this course, we're going to focus on both the matter and the energy in a much more, shall we say, fair proportion. So let's talk about matter first. You already know much of this. Matter takes up space, it has mass, and it exhibits inertia. You know your good buddy inertia. It's why you wear a seatbelt. An object in motion is going to remain in motion until a force acts upon it. And if you're driving down a highway at 55 miles an hour, you'd rather the windshield not be that force that's being exerted on your face. You would rather be wearing a seatbelt that has a strap of cloth holding you into position so that you're not going to make contact with that windshield. Now, matter as we know it on this planet is composed of only about 100 or so different types of atoms. I realize that on the periodic table there are more than 100 elements, but you must remember that uranium is the last naturally occurring one on the planet, and its number is 92. The things that we see beyond that have been basically synthesized in a laboratory. Also, let's talk about our good buddy water. It's always a good place to start because most people have seen water, held water, maybe even used some today in some form or fashion. But water is made up of one oxygen and two hydrogen atoms. If we pass an electric current through water, then we can separate it into its elements, which would be hydrogen and oxygen. Here we have a 9-volt battery along with a condiment cup and two thumbtacks. The two thumbtacks have been very carefully positioned by this gentleman so that they coincide with the exact spacing of the two terminals located at the top of that 9-volt battery. Now note that the tack part is up into the container, and so now the metal heads will come in contact with that battery. Next we're going to fill that cup with water and an electrolyte. Could be salt. I believe in his narration he actually used baking soda. As soon as those thumbtack heads make contact with those terminals on the top of that 9-volt battery, the chemistry begins. We must have charged mobile particles down inside that water. But as time goes by, you'll note that there's a difference in the rate of the conversion of the water into constituent gases. So I'll bet you could tell by the rate of the number of bubbles coming off on the right electrode versus the left electrode which one is the hydrogen versus the oxygen. As time goes by, he's going to actually pan upward up through these tubes that were filled with water and inverted carefully into this electrolyte solution. So that's the actual water that's being decomposed into its constituent gases. And there were no air bubbles at the top when this occurred. So you can now see that there's twice as much gas collected over in the right-hand tube as the left-hand tube the way we're viewing it. So I'll bet you can figure out which one was the hydrogen versus the oxygen. Go ahead, guess. Yep, the one on the right is going to actually have the hydrogen gas in it. Twice as many bubbles, taking up twice as much space, 2 moles versus 1. Reactions can be reversible. I can take two water molecules, run that electric current through them, and I can create one oxygen molecule, written as O2, and two hydrogen molecules, pictured here as two little diatomic molecules, but written symbolically as 2H2. Reactions are also reversible, like I just said. We can take the elements themselves in the proper proportion, a 1 to 2 proportion there, and we can actually have those react, but we'll have to give them some sort of a spark of energy to get this started. Chemistry, defined simply as the study, as I said earlier, of matter and energy, but more importantly what we're going to focus on are the changes between the matter and the energy. So why would you study chemistry in the first place, aside from somebody's making you? That doesn't always make a good reason. But mainly you want to become a better problem solver in all areas of your life. You're going to get to apply a lot of the skills that you've been accumulating up to this point. Some geometry skills, some algebra skills, some vocabulary skills, some writing skills. Don't underestimate the power of a good English course. You also have to study chemistry to be safe, especially in this day and age. We are surrounded by chemicals, not all of which are natural, many of which are synthesized or man-made. So safety could be another reason. Had the Romans understood lead poisoning and understanding that drinking out of lead glassware and eating your food off of lead plates with lead silverware was a really bad idea, then their civilization would not have fallen, or at least have fallen as quickly. We also want to better understand all areas of science. I still love biology and I still love physics. So there are going to be times where I'm going to make connections for you between those two disciplines because I know you are not taking solely a chemistry course in high school and nothing else. You've either had a biology course or you're on a journey to one, and the same with physics. You've either had it at least at some level, maybe even back in 8th grade as a physical science kind of course, but we're going to make those connections and try to make sense of all of the sciences through the lens, shall we say, of chemistry. So I'm going to go very quickly through the scientific method. 25% of your minutes in class should be spent in laboratory. So you're going to apply the scientific method over and over and over again. So you just need to have a plan of attack because you're going to be asked to design some experiments and come up with some procedures and create your own data tables and do some things in what in teacher lingo is called guided inquiry endeavors when it comes to the laboratory. No fewer than 6 of them, by the way, throughout the year. So you need a plan of attack. Well, typically we make observations, then we start to think about those observations and search for patterns. If you're good with finding patterns, generally that helps you in a science course. If you're not good with finding patterns, that's okay. You can observe enough patterns. You can have other people who have figured them out explain them to you. Eventually, you will catch on to looking for patterns. So once you had enough observations and sort of thought about the patterns and some cause and effect, shall we say, if I do this, every single time that happens. If we can do that cause and effect sort of thinking and looking for those patterns, then we can actually generate a hypothesis, which is a possible, not a probable, but a possible explanation for an observation. And then you have to test it. Just thinking about it, unless you're Einstein, isn't going to do you a lot of good. You got to actually get your hands dirty. So you need to actually come up with an experiment and a way to test it. Once you've done that a few times and you're convinced, then you can formulate a theory, which is really just a model. The word theory is kind of overused in our general vernacular, shall we say, the general way we speak to one another. And then you want to test it again and again and again once you've actually formulated this model or this theory so that you can refine it. Now, those are just the fundamental steps. You're going to be doing them quite often. So good experimental design is coupled with repetition, which is key. So good experimental design often means I'm going to hold one thing constant while I vary something else. But if you vary everything else, you're just going to get confusing data. So what you really want to do is hold everything constant but the one thing that you're testing. And that comes with practice. That comes with failure. Everything I know because I did something wrong. That's how I have learned best. Being a huge failure and, okay, perhaps even a bit stubborn because I just keep trying and trying again, has served me quite well. And hopefully you can capitalize on those qualities that some people think of as negative qualities yourself. So again, theory is simply a hypothesis that's explaining why the what happened. This is one of the big moments on any formal lab reports you're ever asked to do. You want to explain why the what happened. The model, well, we use a lot of models to explain natural phenomena. Some are better than others. Almost all models have a flaw. So you're always looking for that flaw and looking for a way to refine that model. But when new evidence is found, that's when we refine it. So like I said, almost all of them have a flaw. And you figure that out when you found new evidence in your model, has a glitch in it. So we're going to run through a little bit of chemistry in terms of, history of chemistry, I should have said, a little bit of the history, and some famous folk you probably have heard in the past, just to brush some cobwebs off from your prior learning. A gentleman named Robert Boyle, as in Boyle's Law, which is right here, Boyle's gas law, P1V1 equals P2V2, or you may have learned it in a fractional format. You're going to, if you stick with me, you're going to figure out that I like linear algebraic equations, partly because they're just easier to type, but also because my brain isolates variables better that way. But you need to put the algebraic equations into a form that works for your brain, not my brain. But Robert Boyle, along with a lot of other those early gas law scientists, they kind of had a hobby, and their hobby was hot air ballooning. And they actually figured out an awful lot about how gases behaved in the atmosphere and down on the surface of the Earth from their hobby of hot air ballooning. So he loved to experiment with air. He actually created the first vacuum pump, which is pretty impressive. He also used it to test one of Galileo's theories, was that it's air resistance that actually makes objects fall at a different rate. In other words, if I took a tube and put a quarter and a feather in the tube, your experience is if I drop both of those objects down this big clear glass tube that you can see through, that the feather would float very delicately and sweetly down to the ground, whereas the quarter would fall like, well, a rock. So if I then hook that clear tube up to a vacuum pump and vacuum all the air out of the tube and drop it again, then you'll see a very different scenario, and it's that they both fall at the same time. Because gravity is independent of air resistance, but your common experience is that you have to be in air to be able to breathe and observe things, and so you're surrounded by air resistance at all times. So Boyle defined elements as anything that cannot be broken into simpler substances, which was pretty insightful, actually. And then we talk about some scientific laws. A scientific law is a summary of observed, measurable, if you will, behavior. And a theory, then, is the why. It's the explanation of that behavior. So the law summarizes what happens. So connect law with what happened. Whereas the theory, and I keep using the word model to get you kind of away from the word theory, but the theory, which is a model, is an attempt to explain why it happened. That's the biggest distinction, shall we say. So some other things that you already know. Law of conservation of mass. The mass of the reactants before must equal the mass of the products after. There is no alchemy here. We are not inventing any new elements or any new substances. So we are obeying one of the many conservation laws that exist in science. Another conservation law is the law of conservation of energy, which you also will learn is the first law of thermodynamics, because we had to give it a fancy name. And all it means is what you've known since about probably third grade. This is the first time you ever heard that energy cannot be created nor destroyed, but can change forms. So if you think about heat energy changing into mechanical energy, like within a steam engine, or if you think about chemical energy turning into mechanical energy, like within the pistons of your internal combustion engine. If it's a V8, it has 8 pistons. So these sorts of things, this kind of thinking has been around pretty much since the dawn of time. Some people credit Aristotle with it, others go to other philosophers, but it's been around and in print for a very long time. We're just still trying to refine it. But scientists are human, and they're subject to all sorts of pitfalls, such as data misinterpretations, purposeful, or people sometimes get a little too creative with their data and publish because they want to be famous, and then someone else tests their findings and finds out, hey, you forged that data. That's never pretty. That's when they've usually formed an emotional attachment to a theory. They just have to believe it no matter what. A loss of objectivity also can come from that same sort of thing, or they could be under political pressure. Their survival depends on it. And then this one often gets in our way. Ego. We all have one. It's just a matter of how big is it. Profit motives. In this country, that's particularly an issue, shall we say. Fads. It's fashionable. Wars. Survival. A lot of our weaponry that has come from a full and complete understanding of chemistry and how things work and, dare we say, don't work, have actually been motivated by wars, the search for a better weapon. And then there are religious beliefs. So all of these things are actually items that affect scientific judgment, because scientists, once again, are human. So when we think about some of these things, and we think about the gas laws that Boyle and others had done, Gay-Lussac, Charles, etc., then we need to have an understanding of the states of matter. And so far, this is probably what you understand, that solids are pretty closely packed, and they are in a a tight arrangement, usually, whether it's in a sheet or whether it's in a coil or whatever it may take form macroscopically. At the atomic level, the atoms are close to one another, or the molecules are close to one another if you're talking about something like plastic. But in liquid, they have more motion. So in solid, they're vibrating constantly. When we add enough energy to it, and kinetic energy is proportional to the temperature, the average, I should say, kinetic energy is proportional to the temperature. That's a proportionality sign. If you're not used to that from mathematics, you will be. And so even when these molecules are very tight together in the solid phase, they're vibrating. Now, if we add enough heat energy for them to actually break free of the solid and liquefy, which is what happens when ice melts, then they are attracted to one another, but they have much more motion. They've gained motion beyond just vibratory motion. Now they have what's called translational motion. They can translocate from one place to another. A fancy way of saying, I left my house and now I'm at school. You translocated from home to school. And then once they overcome any intermolecular forces, anything that's not a chemical bond but is yet an attractive force that's making them stick together, then we can actually vaporize them and make gas molecules. Gas molecules behave as if there's no other molecule around. Now, you're going to see lots of pictures throughout a lot of our work that we do here at the National Math and Science Initiative, because you're going to see lots of pictures in the test questions on the AP exam, and we need you to be thinking pictorially as well as verbally. So you've heard of Galileo. Galileo is kind of an example of some of those religious beliefs and persecution that we were alluding to earlier. Galileo was forced to recant his astronomical observations, which were really remarkably accurate for the time, in face of strong religious resistance. He was known as a bit of a heretic, shall we say. Lavoisier, the father of modern chemistry, was beheaded due to political affiliations. So the need for better explosives, like I talked about a moment ago, rapid change of a solid to a liquid or a gas is what an explosive does, where the diameters of the molecules instantly become about 2,000 times farther apart, and that allows them to exert massive forces on containers and the surroundings. So some of the things that have been somewhat serendipitously discovered, which means it's a happy accident, are fertilizers. They realized that nitrogen was good for lots of stuff, and one of the things it was good for were plants. Go figure, that nitrogen cycle came in handy. So fertilizers that utilize nitrogen, and also nuclear devices, whether they are weapons or whether they are fuel cells that actually can generate power like you could use in your home. So over here we just have, again, some more of the pictorial sorts of representations. When you think about a solid, notice that these molecules have what I think of as a little cartoon motion to them, those little quote marks kind of things around it. They're just vibrating. But once you give them enough energy, they can break free of the very orderly arrangement, and they move a little bit farther apart, not a lot farther apart, but a little bit farther apart, and their motion becomes more, shall we say, frenetic. It's more running around like crazy and bouncing off of stuff. But they still have not achieved as much as these gas particles have. Now, these gas particles are 2,000 times their own diameter farther apart than these liquid molecules. The liquid molecules, you can see, aren't necessarily even one diameter apart. On occasion they are, but they may be snuggled up pretty close to one another. But it's when they're in the gas phase that they have now been freed from is the best way to say it. I was trying to make a verb out of break and it wasn't working out. They've been freed from their intermolecular forces, their attachments, their attractions to one another. So when they're in all of these different phases, you've got to think on the molecular level. So here we have something like carbon dioxide, where these red molecules are the oxygens and this black one is a carbon. So carbon monoxide, you can see here, is doubly bound. It has two bonds holding the oxygen onto the carbon on both sides. But even though it's a linear molecule, and if you don't know what that means yet, you will soon. Even though its geometry implies that it's linear, it's still got vibration. Like if you stood outside and you flapped your arms looking silly like a bird. All right, that's the kind of motion that this is trying to depict here. It also has rotational motion. So even though it has an axis running through the center of that carbon, it can rotate about it in either direction. It can also rotate this way, in that direction as well, whether it's on the, what would it be called, the horizontal plane or the vertical plane. Also, we've got some stretching that happens in carbon dioxide. We have some asymmetrical stretching. Not all stretching is symmetrical. And that's a better drawing of what I was trying to draw. And then we also can actually move from point A to point B. That's called translational motion. So phase change is not quite as simple as you might have thought even an hour ago. All right, so units of measure. You have been beat over the head with the metric system since probably, again, about third grade. It is time. It is time to come to terms with it. And I do not understand a student's resistance to it. Resistance is futile. Your money system is metric. If you know there are 10 dimes, DI, like deci, 10 dimes in a dollar, then you understand the metric system. If you know there are 100 cents, as in centimeter, 100 cents in a dollar, you know the metric system. If you know there's 100 years in a century, you know the metric system. If you know there are 10 years in a decade, you know the metric system. You may not know the metric English conversions. That's different. You can look those up. That's not a problem. But you know the metric system because you can understand money. If you ever get stumped, think about it in terms of money. All right, so units of measure involve two parts. It is always a number and a unit. You don't write many naked numbers in a chemistry class. They almost always have a unit with them. We will celebrate the rare moments that we can say always, and we will celebrate the rare moments when we can write a naked number, because most of the time it's going to have a unit behind it. So two major measurement systems exist still. The English system, which the English don't even use, but the US and some African nations still use the English system. And the metric system, which is what the English, the Brits, and the rest of the globe use. When I lived in England for a couple of years, and it was a little bit of a challenge even for me, who I considered myself fairly well versed in the metric system, to follow a recipe where everything in it was metric when you had English tools. Yes, I gave up and I went and bought some teaspoons. Oh wait, they're not teaspoons. Some spoons that were in the metric system and some measuring cups that were in milliliters. In 1960, a long, long time ago, there was an international agreement that was reached to set up a system of units, so at least scientists, if all the ordinary citizens couldn't get along, at least the scientists needed to communicate clearly, could better communicate, and it was, again, the French, Le Système International, and I just butchered that, so if you speak French, you could do a far better job with that than I can. But it's all based or derived upon the metric system. So the fundamental SI units are listed here. How many fundamental units are there? 1, 2, 3, 4, 5, 6, and 7. This one you've probably never heard of. Luminous intensity has to do with light. It's called the candela. Yes, as in candle. But you have heard of the mole if you've had a chemistry course before. You've heard of amps. That's the fundamental unit of electric current. Then you've heard of temperature. But you live in America where we often talk in degrees Fahrenheit, but you also are aware that there are degrees Celsius, and then there are kelvins. No degree sign on a Kelvin. It's just K. So just remember that Kelvin temperatures are simply the Celsius temperature plus 273.15 if you want to be picky about it, but usually 273 does the trick. And then the rest you've heard of. Time is measured in the fundamental unit of seconds, length is the fundamental metric unit of meter, and mass in the fundamental metric unit of kilogram, because grams are too small. Gram is what 1 milliliter, or about 10 drops of water, weighs. So your numbers get rather large rather quickly, so we deal with them in packets of 1,000, which we call a kilogram. Now this is just to kind of let you get your head wrapped around it. A dime's about a millimeter thick. A quarter is 2.5 centimeters in diameter, which is also really close to an inch in diameter. And the average height of an adult man is 1.8 meters. A nickel has a mass of about 5 grams. A 120-pound person has a mass of about 55 kilograms. For volume, a 12-ounce can of soda has a volume of about 360 mils. And then the prefixes. There is no need to memorize all the prefixes. You just need to know the ones in blue. And some of them you have already memorized out of self-defense. If you understand what a megabyte is on a computer file versus a kilobyte versus a gigabyte, you've already memorized some of these thanks to the computer industry. And then deci, centi, milli, micro, and nano are also becoming more and more commonplace in our everyday language. So there's no real need to memorize them, but you're going to end up doing so out of self-defense. So now let's talk about the different components. Let's talk about volume first. Volume is derived from a length. If you consider a cube that's a meter on each edge, it's going to be pretty big, right? And that would be called a meter cubed. So if you have a decimeter, which is a tenth of a meter, then you would have 1 meter cubed would be equal to 10 decimeters, but that entire quantity cubed. And from your math class, you know that if you've got two terms cubed in there, you're going to have to cube both of them. So you got to cube the 10 and cube the decimeter to come out with 10 cubed, which is 1,000 decimeters cubed. That's a liter. It's also 1,000 milliliters because a decimeter is 1 liter, which is 10 centimeters cubed. So that again means I got to cube the 10, I got to cube the centimeters, so I get 1,000 centimeters cubed, which is 1,000 milliliters, which is also equal to 1 liter. So you have to know those equivalent terms, and you probably already do. Then a centimeter cubed again is a mil, and that's where the gram got its definition, shall we say. Everybody has water. Everybody in the entire planet has access to water. So what they decided to do was just build a cube of a centimeter long, wide, and tall, and fill it with water at its maximum density if you want to be really picky, which is 4 degrees Celsius. That's another discussion for another chapter. But fill it with water, and that volume was called 1 milliliter. 1,000 times that was called a liter. So it really all started from length. Now, mass versus weight. Chemists are very guilty of using these terms interchangeably. So mass is truly the amount of matter in an object, while as weight is a force on that amount of matter, and it has units of newtons. So when we talk about weight in this country, we often talk about pounds. But in physics class or in any science arena, it's going to be talked about in terms of newtons. So it is the response of mass to gravity. Since all of our measurements are going to be made here on Earth, we consider the acceleration due to gravity a constant, so we'll use the terms interchangeably as well. But technically, I just need to be truthful with you and tell you that that's really incorrect. We weigh, note the use of quotes, chemical quantities on a balance, not a scale. Okay, a scale is about putting two weights against one another, kind of like the vegetable scale in the grocery store, but we use a balance in chem class, so we're kind of picky about it. All right, then, gravity. Gravity varies with the altitude here on planet Earth. The closer you are to the center of the Earth, the stronger the gravitational field. Since it originates from the center of the Earth, don't make me explain why. That's not a 25-word or less answer. But every object has a gravitational field, and as long as you're on Earth, your gravitational field is puny compared to that of Mother Earth, so yours is masked. The strength of the gravitational field is proportional to mass. Now let me stop right here for just a second. Think about different times you've seen space travel. And I'm not talking about the movies. I'm talking about NASA. If you've ever seen the astronauts while they're up in the International Space Station or back when the shuttle was flying and they were flying on the space shuttle, they're always moving. And it's, obviously because their craft is moving, the spacecraft they're in. But also, did you ever notice they have to keep pushing themselves off of the walls? Well, that's because in the absence of Earth's big magnetic field, the ship itself is more massive than they are, so it exerts a much bigger gravitational field, and so they are constantly drawn to the sides of the ship, whether it's the top, the bottom, or the sides, because there's no gravity pointing toward the center of the Earth out in space. That's why they have to keep pushing off, and they're constantly in motion. You'll also see on occasion they're drawn toward each other also. So if we take the moon, for example, we've been there as a society. The ship's mass is great. I already did that part, sorry. But on the moon has 1/6 the mass of Earth. So you would experience 1/6 of the gravitational field you experience on Earth. So yes, indeed, therefore you'd weigh 1/6 of what you weigh on Earth. But unless you chop off limbs, you're going to still have the same exact mass. All right, more words that are going to come into your vocabulary when you start dealing with laboratory. There is precision and there is accuracy. Accuracy is what you think it is. Did I get the right answer? Is that accurate? In other words, if you're telling me that that 5 pound sack of sugar should weigh 5 pounds and I mass it and then I do a conversion to get it back into the English system, I should end up with 5 pounds. Precision is how well you repeat the technique. So accuracy, once again, is correctness. It's an agreement of a measurement with the true value. Emphasis on the true value. Precision, however, is reproducibility. Yeah, you can be very precise and not so accurate. It's a degree of agreement between several measurements. If I measure it over and over and over again, am I getting the exact same value each time? Then we have two different kinds of error. That which is random, which we call indeterminate. We cannot determine why it happened. And it's got an equal probability of a measurement being high or low, as opposed to systematic, or systemic, some people say, or determinate, some people say, error, which occurs in the same direction each time. This is usually an error in your device. Your device is flawed. F-L-A-W-E-D, flawed. Doesn't look like that, but that's what it's supposed to say. All right, so let's look at these targets over here before we tackle that problem. The results of several throws of darts show the difference between precise and accurate. All right, so if you see this first picture, I don't see anything on the bullseye, so definitely not accurate, and they're kind of scattered all over the place, so it's not precise either. So it's neither precise nor accurate. However, if we go to the red arrows, what's the story there? They are clustered together, so the person who threw them actually was very precise. But alas, the bullseye is over here, so not so accurate. Now we're onto something. The person who had the green darts, very precise. Threw it the same way in the same general vicinity every single time. And bullseye was very close to the desired target. So both precise and accurate. All right, so now let's look at how that would translate into something you might have done in a chem lab. To check the accuracy of a graduated cylinder, a student filled the cylinder to the 25 milliliter mark using water delivered from a burette. That's that long skinny thing. It has a little valve at the bottom called a stopcock, and it has a lot of gradations between each one of the milliliter marks, so it's very accurate, or so we hope, because we pay a lot of money for them. They can cost like $50 a piece, so be very careful with them in lab. Keep your teacher happy. All right, so what they did is they filled the graduated cylinder to the 25 milliliter mark using the burette. Got to pay attention to the verbs and the prepositions here. From a burette, and then read the volume delivered. So here are the results of the 5 trials. Clearly, they were, think about it, precise. Every time the student filled it to the 25 milliliter mark. However, never did the burette show that it was 25 milliliters. So which one's right? Well, I'm going with the burette. They take a lot more care in manufacturing burettes, which is why they're $50, instead of a graduated cylinder, which is about $3, maybe $5, if it's a good one. So what we have here, though, the fact these do not agree, is actually a systemic error. Systemic error. It could be that the grad is flawed, so the grad itself was not stamped correctly. So is the graduated cylinder accurate? Not at all. Or the 25 milliliter burette, whichever it was. All right, so figures and calculations. Again, I'm hoping that you know a lot of this. I hope I'm not beating a dead horse here, but if I am, fast forward me. I'll never be the wiser. So determining the number of sig figs or digits in a measurement. Non-zero digits are significant, plain and simple. If it's not a zero, then it's significant. Easy enough to identify. A zero is significant if and only if it meets one of the conditions below, just one of them. The zero in question has to be terminating and right. That's a phrase you may want to embrace, terminating and right. Terminating means at the end of the number, and right means to the right of the decimal. The zero in question is also sandwiched, which is kind of self-explanatory, sandwiched between two significant figures. So the only zeros that really are going to give you trouble are those lurking at the end of a number. An exact or counting number, like if I say to you couple, well, that probably brings up a very specific number to you. You have a couple of quarters. How many do you have? 2. If I say a dozen, that brings up a very specific number. 12. We have other words for numbers that aren't so specific. Few. For my mom, one day that meant 3, and the next day that meant 5, and I never could win this game. So exact numbers like dozen, couple, or counting numbers like 8. When you actually say I have 8 balloons. Counting numbers, they have an infinite amount of sig figs, as do fundamental constants like 9.8 meters per second squared for the constant due to the acceleration of gravity. So they don't go into our determination of sig figs. Only things that are measurements. Now, this is not to be confused with derived constants. Later in the course, we're going to talk about K values, like Ka, acid values, and Kb, base values. Those are experimental constants. So you want to make sure that those are distinguished from. So these are what we call derived or experimental constants. All right, so pretty simple exercise here. Give the number of significant figures for each of the following experimental results. The student's extraction procedure on a sample of T yielded. Okay, there's a whole bunch of zeros here, but how many of them are actually significant? For one to be, you always want to go with sandwich first. So this 0 is sandwich, so it is definitely significant. But for those other 2 zeros in question to be significant, they have to be terminating, which means at the end of the number, and neither of them is. But they also have to be to the right of the decimal. So this one satisfies half of that requirement, but it's not terminal at the end. So these are the only digits that are significant. So we have 3 significant figures. A chemist records a mass of. Again, think about a sandwich. Those 2 are sandwiched, so you don't have to worry about them. You're worried about this one, and you're worried about these. Neither of these are terminating. One of them, this one, is to the right, but it's not terminating. It's got to be both. This one is to the right of the decimal and terminating, so yes, it counts. So 1, 2, 3, 4, 5 sig figs. And then in an experiment, a span of time is determined to be 8.050 times 10 to the minus 3 seconds. We don't worry about this in terms of determining the number of sig figs. There's 10 to the minus 3, that's just placeholders. But I look here and I ask myself, is that 0 significant? The answer is yes. We already know this one's significant because it's sandwiched between the 8 and the 5. But is this one significant? Is it terminating at the end of the number? Yes. Is it to the right of the decimal? Yes, it is both things. So that means all of these are significant. 1, 2, 3, 4 of those little suckers. So therefore we have 4 significant figures. You're going to get a lot of practice with that. Now then, more tedium. Reporting the results of a calculation to the proper number of significant figures. When the multiply and divide signs are out, and those are the operations that you're using, then you're going to go with the least significant of all of your measurements given. So it's the least number of significant figures, because that really correlates to the least accurate measurement. So looking at our example here, I have 3 decimal places multiplied by 2 decimal places, so I'm going to answer from my calculator in 2 decimal places. So when you actually run that number, 4.56 times 1.4, I get a whole calculator full of what I call calculator vomit from time to time. But I don't write all that down. I have to think for a moment. Go, yeah, I'm going with 2 sig figs. So the 6 wins, and I look at the 3, I look at the number behind it. It's an 8. That's greater than 5. 6.4 it is. Now when you add and subtract, you do what you were taught long ago, where you line up the decimal places, and the least number of decimal places determines our sig fig. So this is my limiting term. It only has 1 decimal place. So the answer to my addition cannot be trusted beyond that 1 decimal place of accuracy. Now, we won't be doing pH for a while, but you probably remember pH from biology or your first year chemistry course, and the scoop on pH is a little different because pH is a logarithmic scale. I'm just going to keep this simple and tell you because it's a long explanation in the appendix of your text, but because it's logarithmic, the least accurate measurement that you have determines the number of decimal places on the pH. In other words, if I have a pH of 1.45 versus a pH of 12.45, I know on paper, writing them naked like I have, this looks like 3 sig figs and this looks like 4 sig figs. But if these are pHs, they both have 2 sig figs. So the number of decimal places is what needs to correspond to the number of sig figs that you want to report. And then just some pitfalls that students seem to fall into, especially on the first AP Chemistry exam, try to save you from that, is you need to leave all of the calculations on an AP problem in your calculator. Round only at the end. Do not round on the first step and write it down, and then do the next piece of the calculation, and then round that, and do the next piece, and round that. You will round yourself completely out of the ballpark. So round only at the end. This will appeal to your lazy side, where you just get to keep all the numbers in your calculator. Also, examine the significant figure one place, only one place, beyond your desired number of sig figs. If it's greater than 5, round up. If it's less than 5, just drop the remaining digits. So if my number sitting on my calculator had been 6.348 instead of 84, I would have just reported it as 6.3 and just dropped the rest of that because I would be dropping something that's less than half. Also, don't double round. I don't know why students want to do this, but they do. Example, if you've got the number 7.348 sitting in your calculator and you need to round it to sig figs, that again is going to be rounded based on this is 1 sig fig. That's my second sig fig. I look, pretend that looks like an eyeball, looking at that 4, and it's not 5 or better, so I just report it as 7.3. But some students want to look beyond the 4 and say, but it's 4.8. That's really close to 5.0, so I'm going to go ahead and round it up to 4. Because the 8 rounds the 4 up to a 5, in which case then that 0.3 would round to a 0.4. Don't do that. That is wrong. I realize it may have worked because you may have conned a teacher into rounding your final average that way before, but that's not going to work on the AP exam. So be careful with that. All right. You're being a trooper so far. We're almost done. Dimensional analysis. There are many different ways to do problem solving, but dimensional analysis is one of the ones that all chemistry books pretty much talk about. You're going to see whenever we do stoichiometry together that I don't do dimensional analysis as the only method of problem solving, but we do need to know how to do dimensional analysis. So here's an example. Considering a straight pin, as in, ouch, poke me with a straight pin, measuring 2.85 centimeters in length, calculate its length in inches. All right, so start with a conversion factor. There's not a lot of reason for you to memorize conversion factors, but it's a good practice just because you live in a more global society than we once did to know a length, a mass, and a volume. So I have always held on to the fact that there's 2.54 centimeters in an inch, and there's 454 grams in a pound, and mainly because it's a palindrome and I like palindromes, 454. And then that I use 1.06 quarts in a liter. All right, so with conversion factors, once you get that equal sign thing going on, then I can write this two ways. I can say that there's 1 inch for every 2.54 centimeters, or equally correct, I can do the reciprocal of that. Why is this legal? Because both quantities represent the exact same thing, which the thing in this case for us is length. So the conversion factor is exactly equal to 1. So it's the same quantity over the same quantity, which is the same as 3 over 3, which you've known for a long time can be simplified to 1. So to convert the length of the pen, we're playing a unit game. I want to select first one of these conversion factors. Which one do I select, you ask? I want one that's going to have the unit I desire, which was inches, in the numerator. And what I'd like to eliminate from the information given is centimeters. And so I structure it this way. In other words, if I do this one, I'm going to end up with centimeters squared over inches. And that's not what I was told to do. I was told to calculate the length in inches. So I want to cancel those out. And then I just do the math. 2.85 times 2.54, but it's in the denominator, so I'm going to use the reciprocal button because it doesn't get enough props. You see that button right there? That's the reciprocal button. And I come out with 1.12 blah blah blah. But 3 sig figs, that's all I was given, 3 sig figs. So I'm going to answer in 3 sig figs. I'm looking at the calculator. 1.22. Okay, look at this one. Look at that one. That's less than 5, so 1.12 it is. And make sure you put the unit on it. All right, so shall we? A pencil is 7 inches long. Start there. Now, here's a trick. Until you get really good at this and can do all this in your head, it's not a bad idea to, out here at the side, write 3 sig figs. A reminder to yourself so you don't have to think about this again. As soon as you saw that piece of data and it's the only piece of data you're given, then you may want to go with just writing 3 sig figs. I'll write up here so you can still see it. 3 sig figs is what I want when I finish my calculation. Inches. And I want to multiply that by something with inches on the bottom. And if I can get centimeters, great. I just need one of these. If I can't, I may have to do a couple of these conversion factors. So again, I memorized, but we can cheat up here and look. There are 2.54 centimeters in an inch. Inches cancel, which is a good thing. And my unit of the only unit left standing is centimeters, and that's great because that's what I'm supposed to use, so that's good. So 7 times 2.54. 17.78. How many sig figs? Well, this is multiplication. We already determined there were 3. So 17.8 centimeters. It is an excellent idea on the AP exam for you to box your answers. Why, you ask? Because old people score your exams. They like the box. They also like you to write big. They also like to be able to read what you write. So I know you're in a hurry on the AP exam. It's 3 hours long. And by the time you get to having to write any numbers, you've been at it for 90 minutes. So you're a little worn out. But please get in the habit of being neat, big, and boxing your answers. All right. You want to order a bicycle with a 25.5-inch frame. But the sizes in the catalog are only given in centimeters. Alas, what to do? What size should you order? Well, let's start with what they gave us. They gave us 25.5 inches. And I need to get rid of inches. And what do I need to get? Centimeters. So there are 2.54 centimeters in 1 inch. Inches cancel. Answer in centimeters. 3 sig figs. Do you see them? 1, 2, 3 were given to me, so I should answer in 3. So 25.5 times 2.54 makes it sound like a ginormous. That's what the calculator says, but is that what I'm going to write? No. I'm going to go with 3 sig figs, which would make it 64.8 centimeters. Which in reality in a catalog, it's probably going to say a 65 centimeter. I doubt they're going to go to 1/10 of a centimeter in a catalog. But hey, I didn't write the problem. All right, now what? Now, this was a little more complicated. I know this because they're giving me conversion factors. A student has entered a 10-kilometer run. How long is the run in miles? So I've got 3 sig figs that I want to report my answer in. See them? 1, 2, 3. Because that 0 is both terminating and right, the other 0 is sandwiched between 2 significant figures. All right, so essentially you want to think through what you got to do. Well, it all depends on what conversion factors you're given. You're not being asked to memorize any here. They've given them to you. So I'm thinking I can go from kilometers to meters based on this one. And then I can go from meters to yards based on this one. And then I can go from yards to miles. So you have to have a little bit of a strategy there. All right, so shall we? 10.0 kilometers. Now, I'm going to show you a different way this might look. This may be how you may have learned it this way too. Some people just do this instead of writing times like I did up here. And this is perfectly fine. You can do it any way you want. So I want to get kilometers. 1 kilometer I want that out of my life. And I'm going to use 1,000 meters to do that. And then I want meters out of my life. What can I do there? 1 meter for every 1.094 yards. So meters are gone. And then I need to get rid of yards because what do I really want? Miles. So 1 mile, that last conversion factor, for every 1760 yards. I actually knew that one because I'm old enough. Didn't want that to happen. Let's fix that. I'm old enough that I ran track in the days when we ran the 440. Not the 400 meter, we ran the 440 yard. And 4 times around the track, yeah, that was a mile. And so 4 times 440 is 1760 because I was bitter about being forced to run a mile. All right, so now yards are going to cancel. I come out with a mile. It's not a bad idea to circle that just because it helps you focus on the unit separate from the numbers. So I'm going to do the same and clear my screen here. So I'm going to multiply all the way across the top. 10 times 1,000, which I know I could have done in my head and just entered 10,000, times 1.094. There's my numerator, divided by, I can divide by those ones, but they're pointless, right? I'm just going to get 10,940 again. So let's just divide by the 1760. It's the only thing that's going to change that number. Just make sure you type it well. And you come out with 6 point and a whole screen full of calculator vomit. How many sig figs do we need? 3. We'd already thought about that before we got bogged down in this calculation. So 6.2, there's 2 sig figs. What do you figure? What should that last one be? You betcha. I agree. And we're not going to leave it a naked number. We're going to put a unit on it of miles. And there we go. A couple more of these, just for practice. The speed limit on many highways in the United States is 55 miles an hour. God love Texas. We can go 75 in certain spots. We need to start with our 55 miles per hour. And then I need to get rid of miles. So what can I use to get rid of miles? You're not supposed to have these memorized. Go back up here and look. The only thing with mile in it is 1760 yards, so I'm stuck with that. That's still not helping me yet. Don't I need to get also rid of yard then? Yard, 1 meter, I'm getting somewhere now. So 1 meter for every 1.094. That's not very pretty. Can I try that again? 1.094 yards. Okay, so cancel, 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 meters. I can move a decimal, so I'm just going to leave it like this, but if you need to, you can go ahead and put in the times meter, 1,000 of them for each 1 kilometer if you want. Okay, I just move a decimal, but you can do it however you like, whatever works for you. I just reason with it when I'm finished. All right, so what I got? I got meters and I got meters per hour. I'm looking for kilometers per hour, but I can stop here and get meters. So, clear my screen again, just keep it nice and tidy. 55 times 1760 times 1, if you prefer, divided by 1 and 1. So really it's just divided by 1.094. And I get 88483, which is too many sig figs. But that's meters per hour, which I move the decimal 3 places. So that's going to be 88. How many sig figs do I need? 2. If I'm looking back up here at this 55. So 88 kilometers per hour. All right, and then let's look at this last one. A Japanese car is advertised as having a fuel economy, can't say gas mileage, can you, of 15 kilometers per liter. Convert this rating to miles per gallon. So is this going to be a good thing or a bad thing? You might want to think for just a moment. If you drive or have any inkling about cars, what is a good number in miles per gallon? My husband drives an F-150 pickup truck like every good Texas boy does. Yeah, he gets about 12 miles per gallon. That's crummy. I drive a little zippy sports car. I get closer to 30 miles per gallon. And considering she's almost 14 years old, she's approaching a classic now, then that's pretty daggum good. So let's see what this little Japanese number gets. Let's always start with what you have going on. 15 kilometers per liter. All right, now you have to go in search of some other conversion units. There were some others up here, way up here at the top. Right up here. Okay, so let's go with some of those volume ones. Oh, maybe I didn't have one in here. Ah, there they were. Sorry, I went too far. So a liter is 1.06 quarts. I know, I'm making you dizzy. So 1 liter is 1.06 quarts. Okay, now, you think you like the English better than the metric? How many quarts are in a gallon? Because I got liters out of my life, but I got to get quarts out of my life, and I got to get to gallon. So you start by putting them on the same conversion factor, and then you ask yourself, do I know the answer to this? Well, I do. And you do too. Quart. Think about it. Sounds like close to quarter. So how many quarters are in a dollar? 4. How many quarts are in a gallon? Also 4. That's where it got its name, like quarter. All right, then that's got my quarts out of my life. So I've got the kilometers part. Got the gallon. Kilometer where I want it. I got gallon where I want it. Do I have anything else I have to do? Oh, I've got to get to miles. All right, so I know there's 1.094 yards in a meter. They gave us that earlier. And I know from track that 1 mile is 1760 yards. So my yards are out of there. I got my mile where I want it. I got my gallon where I want it. I got a kilometer meter issue going on here. So I need to get rid of both of those terms, but I can do that. Kilometer, 1 kilometer for every 1,000 meters. So meters are gone, kilometers are gone. And I've got miles per gallon coming at you. May run out of room to write it, but I got it there. Okay, so let's punch this sucker in. 15, numerators first. 15 times 1, not worth my time. 4 times 1.094 times 1, not worth my time, but times 1,000 is important. Okay, so there is my numerator, and that is divided by, I'm going to open a paren so I don't screw this up. 1.06 times an understood 1 right there, times 1, times 1760. There's another way to do that. If you're used to hitting divided by and then divided by, that'll work as well. I'll show you that one in a second. Either way, I've got 2 sig figs. That's what I was wanting, 2 sig figs. So I'm going to write 35 mpg. Oops, what happened? That's how it looks like on the sticker on the car, also known as 35 miles per gallon. All right, so I said I'd show you this one. Once I had that numerator term, I could have easily done this as well. Divided by anything that's not a 1. So 1.06, enter, divided by 1760. It's just a matter of your habit and how you were originally taught to do dimensional analysis. Either way, I still come out with 35.18. It's a commutative property of mathematics at play. All right, hang in with me. You're almost done. Temperature. The AP exam does not have you do temperature conversions other than to go from degrees Celsius to Kelvin, and it's the easiest conversion in the whole wide world. You simply add 273 to the Celsius temperature. So the only one that you have to worry about is going from Celsius to Kelvin or vice versa. You want to get Kelvin, you add 273. 0.15 is optional. But there are some general things you just should know just because you're an educated person, not because you're in a chemistry class. You should know the boiling point of water on both the Fahrenheit and Celsius scale, because you can readily get to the Kelvin scale from the Celsius scale by adding 273. So you should know that water boils at 212 Fahrenheit and 100 degrees Celsius, and that room temp is around 20 to 25 degrees Celsius. 68 is a little cool, if you ask me, but a Brit must have done this. They keep their surroundings much cooler than we do here in the U.S. And then the freezing point of water, you should know on the Celsius scale, is 0. That was the whole point. It's Celsius. It used to be called centigrade, meaning 100 markings between the freezing point of water and the boiling point of water. So 100 markings. But now we call it Celsius. I had to make that transition in my life. I was taught centigrade. And then you have to work at memorizing 32 degrees Fahrenheit. Absolute zero, you should also know, is that 273.15, where all molecular motion stops. Just last summer, they actually got something colder than 273.15. They got it down to a little bit less than that. The only thing that will happen is that that number is going to shift a little bit. It's still darn cold. All right, and also notice that a degree of temperature change, emphasis on the word change, on the Celsius scale represents the exact same quantity of change on the Kelvin scale. Finally, because I know you're sick of me, density, mass divided by volume. So determining density. A chemist is trying to identify the main component of a compact disc cleaning fluid. Yeah, you may not know what a cassette tape is. Your children are not going to know what a compact disc is, a CD. They determined that 25.00 centimeters cubed of the substance, which is also known as 25.00 milliliters of the substance, has a mass of 19.625 grams at 20 degrees Celsius. Okay, it's good for you to get in the habit of looking through the problem and marking what these things are. So this is mass. Nope, that's not mass, that's volume. So that's my volume. Put a V. Here's my temperature. And here's my mass. Now, use that information to identify which substance may serve as the main component of cleaning fluid. Justify your answer with a calculation. Well, all they gave me to work from are densities. And the densities vary quite a bit based on those substances. So I'm going to figure out the density given the data that they gave me and see how it goes from there. So density is equal to mass divided by volume. And the mass was 19.625 grams of the substance, which had a volume of 25.00 centimeters cubed. And so 19.625 divided by 25. You can do the 0.00 if it makes you feel better. 0.785. How many sig figs do we need here? Ooh, look at all those. 1, 2, 3, 4, 5. 1, 2, 3, 4. Let's go 4. So, from that calculator, 0.7850 to get that fourth sig fig on there. Grams per centimeter cubed. So then you stand back and you go, okay, I'm done. No, you haven't answered the question yet. Use the information to identify which substance may serve as the main component of the cleaning fluid. I have to think a little harder. So what's the story? Well, with that density, it is closest to this substance, which is isopropyl alcohol. So I have to answer the actual question, isopropyl alcohol. All right, and then we covered a bit of this earlier, but just once more with feeling, mostly vocabulary lesson, be very, very, very clear through this entire course that changes of state, meaning solid, liquid, gas, involve altering intermolecular forces, not altering actual chemical bonds. Bonds are not broken. When you were a little kid, you might have thought when water was boiling that there was hydrogen and oxygen gas in the bubbles, but no, 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 and dare I say no, that's not how it works. It's water vapor in the bubbles. It's gaseous H2O, not hydrogen gas, oxygen gas. If you want that to happen, we're going to have to put an electric current through it, like you saw earlier. All right, so solids are rigid, definite shape and volume. The molecules are close together, and they are vibrating, and that's all they are doing about fixed points. They are virtually incompressible because they're so close together. Liquid has a definite volume, but it takes on the shape of the container. The molecules still vibrate, but they also have additional rotational motion. They can rotate on their own axis, and they can move from place to place, which we call translational motion. They can slide past one another, but they're still very, very close together. So it is slightly compressible. That's what your brake fluid is in a vehicle. When you press on a hydraulic brake pedal, it's actually compressing a fluid, so they are slightly compressible. And then gas has no definite volume, takes on the shape of the container. Molecules vibrate, rotate, and translate, meaning go from point A to point B, and are independent of each other. They're not aware that any neighbors are around because they're very far apart, 2,000 diameters farther apart. I know you can't read that very well. It says farther apart. They are, however, highly compressible. Vapor, just to be clear on these terms when you see them, vapor is the gas phase of substance that I said earlier is normally a solid or a liquid at room temperature. Iodine vapor, iodine is normally a solid, but it sublimes. Carbon dioxide is a solid, but it sublimes. That's what dry ice really means. It doesn't make a puddle. It goes straight from solid to vapor. So we talk about carbon dioxide vapor. But there's also carbon dioxide gas because it's a gas at room temperature. But if you've got a chunk of dry ice, you see that fog coming off of it, we call that stuff the vapor of it. And then a fluid is anything that can flow. So all gases and liquids are called fluids. Mixtures, you've already known from years past, are physically separated. So we have homogeneous and heterogeneous. Homogeneous have visibly indistinguishable parts. Solutions, including air, which is a solution of gases. You don't think all solutions have to be wet. Concrete is a solid solution of cement and pebbles. Heterogeneous have visibly distinguishable parts. That means we can physically separate. So filtering, you're going to do all of these in lab. Fractional crystallization and distillation, along with chromatography. One of the first labs you'll probably do is this one. Are all ways of physically separating the parts. When you filter, you put a piece of filter paper in a funnel and you separate out a solid from the surrounding solution. So paper chromatography, and you may have done this in biology with chlorophyll, I hope you did at some point. You essentially put ink or a pigment of some sort or a dye of some sort on this piece of paper that you have pre-marked with a pencil. So you put a pencil mark right there so you can track its progress. And then you let it rip. You put it down into a solvent of some sort, and there's a whole art to selecting solvents. We'll cover that when we do the lab. And essentially this piece of chromatography paper is going to act like a wick, and it's going to wick up or sop up against gravity. It's going to crawl this solvent, this wet stuff down in here, this aqueous solution. It's going to crawl and wick up that chromatography paper. And while doing so, it's going to start to separate its pigments. And then you can measure and get a ratio of that starting line, which we call the RF. Well, I don't know that we call it the RF. The RF is more the ratio. But it's the starting line versus how far it traveled is the ratio to get our RF value. So pure substances, compounds like water, carbon dioxide, and elements, they can be separated by chemical means. So electrolysis that you saw earlier with water is a common chemical method for separating compounds into elements. So the elements can be broken down into atoms, which can be further broken down into nuclei and electrons, which the nucleus can be further broken down into protons and neutrons, and the electrons in the electron cloud are outside it. And then we could actually go all the way down to the subatomic particles that make up protons, neutrons, which are quarks. Notice there are no quarks with the electrons. So this is just a nice little flowchart that kind of helps you organize your thoughts about such things. All right, that's it. That's 1/3 of your summer assignment. Down the tubes. Ready, signed, sealed, delivered. It's gone. You probably knew most of that already, huh? I'll try to teach you some new stuff next time. Again, my name is Renee McCormick, and I hope you have a great rest of your day.